So we have a very low error rate, but it's not perfect. So every time your cell divides, again, over time, you're going to accumulate these mutations because we do not have a zero proofreading rate. This is why you can accumulate damage to your DNA over time. And any cell that has a mutation, every time that cell divides, the daughter cells will inherit the same mutation, okay? You're not giving it to your children, but you are accumulating mutations in your own cells. If you have a mutation in your gamete, you can give that to your children. So any mutations that occur in your sperm or your eggs is passed down to your children. Somatic mutations just put you yourself at higher risk of cancer. Most of the mutations either do nothing or are problematic. Occasionally you get a mutation that's an advantage, and that is the material upon which natural selection works. If we didn't have any mutations, we wouldn't have natural selection. You've got to have a little bit of differences in each member of the species to have all of these different options for natural selection to move the species forward from an evolutionary standpoint. Okay. Oh, here's another little issue I haven't talked about yet. One last little troublesome thing if you are replicating DNA. It still has to do with this whole problem that DNA polymerase cannot attach any new nucleotides to the 5' end, only the 3' end. And this only is true if you have linear DNA. This isn't true if you have circular DNA. But if you have linear DNA, there's always going to be a 5' end that has an RNA primer that the DNA polymerase cannot go back in and fix. And the idea here, so you can see here, we're replicating a linear sequence. So here we've got the parent strand in the 3' to 5' direction. And so we've got an RNA primer here where we've made an Okazaki fragment. And this RNA primer cannot be replaced by DNA because we cannot put DNA at the 5' end. We can only put DNA at the 3' end. So the very tips of the chromosomes are going to have RNA. And we can't replicate RNA the way that we replicate DNA. So when we go to replicate this strand, we're going to have this short little sequence where they remove the RNA primer, but we don't have anything here. So when we separate this daughter strand, you know, this is the first round of replication. In the second round of replication, both strands are going to be shorter, again, because we have a new leading strand that's shorter than the original parent strand here. So when this 5' end is short, goes to replicate, we're going to have one short, you know, set of DNA, and then we'll have one that has this kind of ragged edge, just like up here, we have this ragged edge. So if you think about it, you have a cell that starts, every time the cell divides, you're going to be getting shorter and shorter at the ends of the chromosomes. You'll have one short end, and then you'll have one that's raggedy. So you're going to get these raggedy short ends to your chromosomes. This can be a problem. Because what if there's important genetic information at the ends of your DNA, okay, for your linear DNA? So what we have to protect ourselves from this is called a telomere. And my best analogy when I think about what a telomere is, you know how you have a shoelace, and the shoelace at the end can get raggedy, except that we have these little plastic caps on the ends of our shoelaces that keep them together. If you lose that plastic cap, all of a sudden the ends of your shoelace fray. That's basically what a telomere is. And all the telomere is actually repeating sequences. You can have 100 to 1,000 repeats of like a six nucleotide segment. And I think it's TTAGGG, but don't hold me to that. I can't remember exactly. But it's 6 nucleotides in a row over and over and over and over and over again, hundreds to thousands of times. It does not code for anything, but basically it protects the important genetic information. So the cell, every time the cell divides, the telomeres, the ends of the DNA are shortening. The telomeres are getting shorter and shorter and shorter. And at a certain point, they get short to the point that the cell says, I've divided too many times. I might have accumulated a lot of mutations that could be harmful to my host. I will now commit suicide. I will take one for the team. So that's why cells are not immortal. They can only divide a certain number of times before they go kaput because their telomeres shorten too much. But it protects that important genetic information. And actually, there is an enzyme that will keep telomeres always the same length. So every time they shorten, there's this enzyme called telomerase that will re-lengthen the telomeres. This enzyme is really important in our gametes because it keeps our gametes from shortening too much, so we don't lose genetic information in our gametes cells. So this enzyme should be active in gametes. It should not be active in other cells because we want other cells to divide after they've divided a certain number of times. We want them to die. And sometimes activation of this enzyme inappropriately, when it's not supposed to be active, is associated with certain cancers again because it makes the cell immortal. That's my cell phone. Sorry guys. I thought it was off today.
Do you have a Spanish ringtone?
Only for my husband, he's Spanish. So he gets his own special ring because he always fusses at me because I don't ever answer my phone. But he helped me do an anatomy lab this morning, so I had my phone on so that he could find me in the anatomy lab. Okay, but we'll go back to telomeres. So this is just pointing out, this is what a telomere is. It's basically just a sequence of non-coding DNA. It's just a long sequence that protects the actual meat of the chromosome, the actual coding. This is how you make a protein information. So these telomeres, they don't prevent the DNA from shortening. The DNA is still shortening, but it's shortening in non-essential genetic information. It's just shortening that sequence of TTAGGG, TTAGGG. So it's also associated with aging. So for a while, people were like, "Ooh, if we can keep our telomeres long, we can be immortal." Problem is, you can also get cancer. So pick your poison. And have immortal cancer. Sounds terrible. So telomeres don't prevent the shortening of DNA. They just postpone the erosion of the important genetic material. And again, shortening of telomeres is thought to be connected to aging. So there is a lot of studying that's going on and trying to figure out how do you keep aging from occurring while also not fostering cancer, because again, the more a cell divides, the greater the likelihood that we've got some mutations, because the mutation rate is about 1 in every 10 billion. And if we've got 3 billion base pairs in our DNA, so we're making 6 billion new base pairs every time a cell divides because we're making 2 copies. You can see that you can start accumulating errors after a few rounds of replication. So we want the cells to die, but we don't want to age. But this is just a cool image where they've stained for the telomeres. So you can see the telomeres at the end of each chromosome. Okay, and so where they're really important, where this enzyme's really important, is in your germ cells. The germ cells are the cells that are going to give rise to your gametes. Because basically, every time a germ cell divided, it would shorten and shorten and shorten. And you want your germ cells to maintain the entire genome. So basically, all of these essential genes that are at the end of each chromosome would get eroded and eroded and eroded every time your germ cells divided via meiosis. So we need to keep those chromosomes at the full length. So this is where this enzyme comes to play. This telomerase enzyme is going to work in germ cells to lengthen the telomeres every time they shorten. So they shorten, telomerase lengthens them. They shorten, telomerase lengthens them. So they always stay the same length. And then when those cells start dividing in a human via mitosis, a developing individual, then they shorten and shorten and shorten, but don't return to that full length. But meiosis, we want to restore that full length. You don't want to lose the genes at the end of the chromosomes. So that's why it's important in germ cells, but it's also pointing out that that's also thought to be how it protects us from cancerous growth, because it causes cells that have divided multiple times to initiate apoptosis, which is programmed cell death, so that you don't accumulate enough mutations to increase your risk of cancer. Okay. And then our last topic, and we'll be finished today. We gotta move fast to these last 2 chapters, so buckle up and read in advance. But the last topic that we're going to discuss really quickly is just how do we actually fit all of this genetic information in our nucleus. And this is actually a topic we've already referred to. I just want to point out a few new things about it. We've got, if we unrolled the DNA that's in each of our nuclei, we would have about 6 feet. If you unwind it all, it would be about 6 feet tall. It's taller than me. In each nucleus of every single cell in my body. That's a lot of DNA, all right? So we've got to figure out a way to condense it and compact it. But another thing you have to think about, we know that the most condensed state is when we have a chromosome. You can't access any of the information if it's all coiled up. Okay, when you hypercoil all that DNA and it's all balled up, and you want to, say I need to transcribe a gene, but it's all in the middle here. It's way in the middle of the DNA that's all compacted. You can't access the genetic code when it is tightly coiled. So we have to have these different states of being coiled and uncoiled so that we can actually access the information that's coded in the genome. So a few things to think about. We have a lot of proteins that are also associated with our DNA. And when you talk about DNA plus protein, we call that chromatin. And basically the chromatin is going to consist of